Okay, so this is the general energy balance equation that we wrote in the previous video. And what we know about this is that it's applicable to all systems. But as we saw at the very end, in many cases, we're interested in um, designs where thermal processes or thermal considerations are going to dominate. So things like the internal energy, things like the enthalpy are going to be the most important terms, and things like the kinetic energy, the macroscopic kinetic energy, and the macroscopic potential energy are not going to change very much, and so we can neglect those terms. So things like maybe exothermic reactors, distillation columns, heat exchangers, those are the sorts of things where those thermal processes are going to dominate. On the other hand, we have a whole collection of problems, right, where thermal properties or thermal processes are not going to dominate, are not going to be necessarily that important. And so we can take this same equation, right, and if we neglect or minimize the thermal terms and keep the potential and kinetic energy terms, then we can derive what's known as the mechanical energy balance. And this is useful for things like fluid flow in and out of tanks, for pump systems, for frictional losses, for things where we're moving fluids around and the mechanical forces on them are going to dominate versus the thermal processes. So in general, right, I can look at writing this equation in terms of deltas, right? So if I have delta U plus delta PV plus delta V squared over 2 plus delta G delta Z is going to be equal to Q dot plus W, right? And I want to focus a minute on the delta PV term, right? So if I expand this, this is going to be V delta P plus P delta V. And for an incompressible fluid, which most liquids are, right, delta V is going to be 0, right? And actually these are all divided by mass, right, because we divide it through by mass. And what I'm also going to do is I'm also going to replace volume here by 1 over density, right? So if I then gather terms that are similar or important, right, what I'm going to see is I get delta P over rho plus delta V squared over 2 plus G delta Z plus delta U plus Q over M is equal to the shaft work, right? And so this is our pressure change term, right? This is kinetic energy. This is potential energy. And for mechanical systems, this is typically what's lumped together, right, as frictional forces or frictional losses, right? Frictional heating in this case, right? Fluid moving through a pipe will lose energy due to friction, and that often then is lumped together as a dissipation in terms of a small amount of heating and changes in internal energy, right? So we lump that together as frictional forces, and then the sum of these three things is equal to the shaft work, or the work that's imposed on the system, right? So this then basically becomes our mechanical energy balance, right? Changes in pressure between two defined points in the system divided by the density of the fluid, plus change in the velocity of the fluid, plus the change in height of the fluid, plus the sum of all of the frictional forces, which are typically done by correlation, is equal to the shaft work, right? So this is an energy balance that we can use in systems that are not thermally dominated, that are more mechanically dominated. If we want to simplify this even a little bit further, right, we can make another couple of assumptions, right? And the Bernoulli equation does exactly that, right? It basically says that the Bernoulli equation simplifies and says the sum of the frictional forces, or frictional forces, are essentially negligible, And it also says that we're not imposing or doing or extracting any shaft work on the system. And so you can see that if we simplify it in that fashion, that the Bernoulli equation basically boils down to changes in pressure plus changes in velocity plus changes in the gravitational field of the height have to equal 0. And this is a very simplified version, but also a very useful version for how fluids can be moved around. And you can see that it basically involves the interplay between pressure of a fluid, right, which is a form of storing energy in the fluid, the velocity of the fluid, and the height of the fluid, right? So you can see how if I wanted to, for example, pump fluid from a low point to a high point, right, from here, right, how would these three things interplay, right? So this is delta Z, right? And so this would basically, this equation would tell me how the pressure, velocity, and height all are related for moving a fluid from, say, this point to this point, which is a very useful thing in many chemical systems. So you can see how this equation, the Bernoulli equation, is derived from the mechanical energy balance, and the mechanical energy balance is just a simplification or a special case of the general energy balance that we derived from an arbitrary system with an arbitrary number of inputs and outputs. So if we keep that general equation in mind, we can always simplify it in different ways to fit the system that we're interested in looking at, whether that's a system that's thermally dominated and we can discard kinetic and potential energy terms, or whether that's a system that's mechanically dominated and we can discard or downplay the thermally dominated terms. So all of these will hopefully be really useful as we go through and start applying energy balances to different types of systems.